morning, good afternoon, good evening to everyone. It is a great pleasure for me to welcome you to my talk in the LatinX workshop at CVPR 21 Virtual. My name is Pablo Arbeláez. I lead the Center for Research and Formation in Artificial Intelligence at the Universidad de los Andes in Bogota, Colombia. Let me first describe our center. We are located in Bogota, Colombia, in the northern tip of South America, just above the equator. Our city, Bogota, is located in the Andes. That's the reason for the name of our university. Our university is consistently ranked among the top 10 universities in Latin America. We are a small private university oriented towards research, and our School of Engineering has 8 departments in the diverse fields of engineering. Our center is called Center for Research and Formation in Artificial Intelligence, CinfonIA for its acronym in Spanish. We're proud to be the first academic center for AI in the region. CinfonIA's work is based on 3 pillars. First, academic excellence, which is the trademark of our university. Second, responsible research. And third, ethical principles. Based upon these 3 pillars is our mission, which is transforming the world with artificial intelligence for the benefit of humanity. We are about 25 professors from very different backgrounds and departments, and the center unifies the work some of us have been doing for several years or even decades at the university in topics related with AI. At CinfonIA, we conduct research in 3 main topics. First, we have multiple projects in global health applications. Second, we have a large area of application in sustainable development. And third, our main technical expertise is in computer vision. Of course, in order to be active in such diverse domains, our research has the support of a strong network of international collaborators. Among them, some of the world's leading institutions and companies. We devote a significant fraction of our research efforts to global health applications. We have 6 main projects in this area. The first one is on automated diagnosis of congenital heart diseases. Our second health application is in early lung cancer diagnosis. The next application is on machine learning for massive COVID-19 testing. The next project is a very surprising application of modern computer vision techniques on drug discovery. The 5th project is on robot-assisted surgery. Finally, in this talk, I will focus on a very important application of modern computer vision techniques into medical image segmentation. Our second main area of application in CinfonIA is sustainable development. Most of my colleagues work in this area, and we have projects in topics such as learning for society, social robotics, learning for education, semantic web, and also industrial application. Within artificial intelligence, our core technical expertise lies in the field of computer vision. I have contributed to different classical problems in our field, such as segmentation and grouping, visual recognition, and also on video analysis. More recently, since I came back to Colombia, I have been active in these fields, and also we have pursued a collaboration with the University of Freiburg in video segmentation. Last year, we had a collaboration with Adobe Research in active speaker recognition, and we won the challenge here at CVPR in 2020. We are also now part of the EGO4D University Consortium, led by FAIR. Recently, we have also been very excited by new fields and problems within computer vision. In particular, we're working on vision and language in collaboration with Google Research Zurich, We have also a very active collaboration with ETHZ in the field of image and video generation. And finally, a very recent topic, which I personally think is very interesting because it may hold the key towards interpretability in the deep learning models we train. It is adversarial robustness, and we are collaborating with the group of Bernard Ganem at KAUST in this program. The first project I will present is at the intersection of computer vision and natural language understanding. This work is a collaboration with Google Research Zurich. It is called Panoptic Narrative Grounding, and we address the problem of visual grounding of natural language expressions. Several experimental frameworks have been proposed to study the problems at the intersection of vision and language. Most of them contain very dense language annotations, such as visual genome on the left, but their visual annotations are very sparse and rough, either bounding boxes on visual genome or on the right on CocoRef, just a single binary segmentation mask. We propose panoptic narrative grounding, which is a spatially finer and more general formulation of the task. Given an input image like the one on the left, with an associated caption, like this one on the bottom, our goal is to produce a panoptic segmentation that grounds its visual objects densely, as we can see on the right. We use segmentations instead of bounding boxes, and we include all panoptic categories to fully exploit the intrinsic semantic richness in a visual scene. This table summarizes the characteristics of existing datasets at the intersection of vision and language and compares them against our proposal. Our benchmark dataset is designed to fill the gaps between all previous datasets. First, in terms of granularity, as it maintains the finest granularity over language by grounding specific words in a narrative. Second, in terms of visual granularity, as it provides fine-grained visual grounding annotations using segmentations. Finally, our annotations include panoptic categories instead of just focusing on things categories, which gives way to a global analysis of the scene, which is relevant for reasoning about the world around us. Our starting point is localized narratives, a multimodal dataset for visual grounding based on the natural human task of describing images while simultaneously pointing with the mouse at the regions being described. We can see an example here. We transfer the localized narrative annotations to COCO panoptic segmentations by selecting a segmentation region for each noun in a caption according to a timed trace points and discriminating by the segmentation mask category. We can see here some examples of transferred annotations for COCO images. We can observe the input image and the localized narrative with this color code that represents the order of the words within the caption. Then, on panel C, we can see the result of our annotation transfer, a dense grounding of the textual description. Here is another example in which you can observe that our technique is able to cope with free-form motion from the users. Here we can see some other examples. Our annotation transfer methodology leverages the time and spatial correspondences between verbal captions, mouse traces, and image regions to provide fine-grained visual grounding annotations. Another example here. We now have a dense grounding that is synchronized with the different nouns in the caption. This will be the annotations for our task and the expected result of automated methods. For quantitative evaluation, we propose to calculate the average recall. This metric considers different intersection over union thresholds between the panoptic segmentation proposal and the ground truth. Hence, both the accuracy and the quality of the segmentations affect the method's performance, since the intersection over union metric determines whether a detection is considered a true positive or not. The final metric is the area under this curve. We now have ground truth annotations and a quantitative evaluation metric for our task. Our next contribution is a baseline technique for panoptic narrative grounding. Our model takes an image and a corresponding caption as input, followed by a top-down approach by extracting panoptic segmentation proposals with a backbone segmenter. Sequentially, we use single modality transformers to independently process the segmentation proposals and the tokens from the caption. We then jointly process the two branches output with a cross-modality transformer. Finally, we calculate an affinity matrix between the visual and textual information and select the more relevant panoptic segmentation proposal for each word. Our final output is then a panoptic segmentation in which each segment is associated to one of the sequential nouns in the caption. Here we can observe some quantitative results. In this plot, the x-axis is the overlap and the y-axis is the recall of matched segments. We can see that our method has a drop of only 9 absolute average recall points with respect to the upper bound performance given by the baseline panoptic segmentation method with an oracle that assigns perfect matchings. This result suggests that our proposed baseline is very strong and a good starting point to promote research in this task. We can also disaggregate the performance of our baseline method into thing and stuff categories. We observe a gap of 5 absolute average recall points between the results in the two types of categories, things being harder than stuff categories. We hypothesize that this gap is due to, first, greater variations in position and appearance in things categories, and second, because the model must disambiguate between the instances of a given category and select the one to which the noun refers in the captions context. We can gain further insights by separating performance on singular and plural nouns. The drop in performance for plural nouns, despite having a higher upper bound, indicates that our model does not retrieve all the instances of the object to which language refers. We can see here some qualitative examples of our baseline method when compared to the ground truth panoptic segmentations of our benchmark. These first examples show some of our results with high accuracy. Remember that the output of our system is the panoptic segmentation and an association of each segment to one of the nouns in the caption, here represented by the color code. We can see here another example in which the system successfully performs the task despite having a relatively complex scene and a long caption. We identify two main failure modes in our baseline model. First, it sometimes fails to disambiguate between instances of the same category within the scene. In this case, it fails to distinguish between the giraffe that is sitting and the one behind the trees, hence performing an incorrect matching, although the segmentation is correct. It is therefore not enough to have the correct categories to perform well in our metric. Here we can see another example in which our baseline model struggles with the plural nouns like the people sitting in the bottom example. The next project that I will present to you is about robust super-resolution. The title of this work is Generalized Real-World Super-Resolution through Adversarial Robustness. This work is done in collaboration with Luc van Gool's group from ETH Zurich. Super-resolution is the task of increasing the resolution of a given image, as we all know. One of the sub-areas of super-resolution is called real-world super-resolution, which attempts to solve the more specific problem of removing real-world corruptions, such as JPEG compression or sensor noise. Here we show a visual example of the difference between low-resolution images of the traditional super-resolution task and real-world super-resolution. Note that in traditional super-resolution, the input images are clean. In contrast, both real-world images include noise and corruptions. Furthermore, each real-world super-resolution dataset exhibits a different type of corruption. In this particular example, the entire 20 dataset includes color alterations in random pixels throughout the image. In contrast, the M19 dataset on the right includes JPEG compression artifacts. The main motivation for our work is the lack of generalizable real-world super-resolution methods among the state-of-the-art techniques. On the one hand, traditional super-resolution methods fail to produce high-resolution results in degraded inputs. On the other hand, the state-of-the-art methods for real-world super-resolution have modules to learn the specific noise of each dataset. Thus, these methods fail to generalize across different types of datasets. In contrast, in this work, we leverage adversarial attacks to create real-world SR models which are robust to unseen noise types. Here is an example of a state-of-the-art real-world SR technique based on generative adversarial networks. The most successful strategies in state-of-the-art techniques, the one that wins the challenges, is to include, during training, a handcrafted noise model that mimics the noise in the target dataset. Our main idea is to replace this handcrafted noise model by an adversarial optimization module. Hence, during training, we learn the specific noise that will confuse the GAN when performing the super-resolution task. In this way, after convergence, our technique learns a super-resolution model that does not depend on a specific type of noise. It can hence generalize much better to other datasets and types of degradations. To our knowledge, this is the first time that generative adversarial networks and adversarial robustness have been successfully combined. We call our technique robust super-resolution. In detail, we learn with adversarial examples generated on the fly with the projected gradient descent method. We take inspiration from a state-of-the-art approach to design structured noise by grouping pixels. Yet, during the optimization iterations of the attack, we no longer control the noise structure, as it changes according to the steps of the gradient and the input data. Once we have constructed the adversarial examples, we perform the standard min-max optimization process with the generator and the discriminator to train the GAN robustly. We evaluate our method in two datasets with very different synthetic corruptions. We compare our results against the top state-of-the-art methods for real-world SR that need a specific model for each dataset. And we also include a baseline method that is not trained with adversarial examples. Next are the super resolution results of our method, and the last column will show the ground truth high resolution image. Here, blue frames denote training and validation on the same dataset, while red frames denote training and validation on different datasets. The green frames show our method that was not trained on any of the corrupted datasets. Note that we achieve remarkable results in enhancing details and removing noise for both of the validation datasets. Here is another detail where we can observe the same features. In this example, we can see that the state-of-the-art methods lack the capacity of generalizing through multiple datasets. In contrast, our approach creates photorealistic results regardless of the type of noise in the input image. We also test our method on a real-world dataset that does not include ground truth HR images. Note that none of the methods was trained on this specific dataset, and the state-of-the-art techniques all fail ungraciously. In contrast, our method produces realistic super-resolution results even though it was not trained on a specific phase dataset. The last project I will highlight today is on medical image segmentation. This work will be presented in MICAI 2021. This is a sneak peek you're getting, and it was partially supported by a computational research grant by Amazon Web Services. Diagnostic images are critical in modern clinical practice. However, their visual inspection can be really challenging. First, it requires years of training to accurately assess different pathologies in this data. Additionally, the assessment is observer-dependent and in some cases can be subjective. Moreover, these are very tiring and time-consuming processes for very busy specialists. Finally, the most commonly used diagnostic images are three-dimensional volumes, which add a significant difficulty to their navigation and visual inspection. There are two main types of problems one is interested in this field. The first is automatically segmenting different organs. Those usually have constant shape and location within the 3D scan. They tend to have large size, and the difficulty lies in their diversity. There can be many different organs with very large variations in their appearance. The second task is to segment lesions and, in particular, tumors. Tumors usually have irregular shape. They have an unpredictable size and location within the image, and they may or may not be present. There are three main imaging modalities typically used in this field: standard X-rays, MRIs, and CTs. The last two, of course, have the advantage of being three-dimensional volumes and hence providing richer information. One of the main difficulties in this field lies, of course, in the very limited annotations we have. Annotations here must be performed by trained specialists who are typically very busy. And finally, processing these large volumes requires high computational power. Also, the task of segmenting medical images is central to the MICAI community and has been studied for many years. Most methods are specific to a particular organ or type of lesion. The task of general medical image segmentation has only been studied in the last couple of years, and that is thanks to the development of the medical segmentation decathlon. This benchmark and challenge includes 10 tasks from different structures and pathologies. Those were individually existing datasets that were regrouped for the decathlon. Together, the dataset provides more than 2,600 patients with multimodal scans. It is therefore an appropriate benchmark to develop general segmentation methods. However, the problem of adversarial robustness has not yet been studied in this very important application domain, and that is the main purpose of this work. The CVPR community understands, of course, the importance of adversarial robustness for deep learning systems that will be deployed on the real world. However, one may wonder about the importance of these issues in the medical domain. The reasons to care about adversarial robustness in the medical domain are the same as for natural images. First, there is a concern about security, as hospitals have centralized information systems that are vulnerable to cyber attacks, as most institutions nowadays. Second is the need for interpretability. In the case of diagnostic images, this characteristic is critical because lack of transparency in decision-making processes reduces the trust in automated methods and hence hinders their deployment in real-life scenarios. And as we know from the computer vision literature, this type of adversarial training can significantly improve the interpretability of deep learning methods. Our first contribution in this work is a method for generic medical image segmentation that we call ROG. Here is an overview of its architecture. Our model uses a single lattice architecture that is capable of generalizing well across the different tasks of the medical segmentation decathlon. Moreover, it is light and easy to train, which is a critical feature for studying adversarial robustness. One first sanity check is to evaluate our approach on the clean images of the medical segmentation decathlon test set. We can observe that ROG obtains competitive results in most tasks against the state-of-the-art methods, which are not many. In particular, each of them has their own issues that prevent their implementation for our purposes. Compared to MPUNet, ROG is capable of generalizing better across the medical segmentation decathlon. NoNeNet is actually not a single architecture, but an ensemble of multiple models for each of the 10 tasks in the decathlon. Finally, this technique was optimized through expensive neural architecture research and doesn't have publicly available code. Our method obtains competitive performance with a single light architecture on all of the MSD tasks. Therefore, it is a strong baseline to study adversarial robustness in medical segmentation. We can see here a quantitative comparison between our method ROG and one of the state-of-the-art techniques when both are trained on clean images. The performance on clean images, what we were looking at in the previous slide, corresponds to the leftmost point in the two curves. In the x-axis, we have increasing levels of adversarial noise. We can see that as the noise increases, performance for both methods decreases quickly, and there is not a statistically significant difference between them. The results show the vulnerability of state-of-the-art generic medical segmentation methods to malicious adversaries. In our experiments, we extend the state-of-the-art auto-attack framework to this setup in order to ensure that our adversaries are the most recent and malicious ones. In blue, we can observe the performance of ROG when it is trained with adversarial examples. In particular, here we used FreeAT as source of adversaries. We can observe a large gap between the protected and unprotected models, showing that our defense mechanism is effective, increasing the area under this curve from 0.3 for the unprotected methods to above 0.4 for the protected model. However, we can also see that performance decreases from around 70% on clean images to around 20% for the protected model, implying that there is still a large margin for improvement in defending medical segmentation systems. Here we can observe some qualitative results. In the case of colon cancer, you can see here the annotations in one slide of the volume and the prediction in clean images of both our method and the state-of-the-art technique. In both cases, we obtain very reasonable results. However, when the unprotected model is under attack, it produces arbitrary results, while ours is more resilient. Here is a different example in liver and liver tumor, in which the tumor simply disappears in the unprotected model. You can imagine the implications of such a failure in the clinical practice. Here we have a different structure, the hippocampus in the brain, highlighting that our same technique can produce all these diverse results when properly trained. Finally, an example in long nodules in which the adversaries significantly increase the size of the prediction for the unprotected model. Remember that each type of mistake, either false positives or false negatives, can have life and death consequences in this domain. This is the web page of the project where you can get more information. And this concludes my talk. Thank you very much and please enjoy the conference. Muchas gracias y disfruten CVPR. Hi everyone, it is a pleasure to be here. I think Gilberto is having some connection issues. I hope he will be soon here to convey the questions.
Yeah, sorry, I was having some problems. I was saying that I just learned that that you're actually in the audience. So I'm sorry if you wanted to make your presentation live, because I think it was okay. Okay, thank you. So, is there any questions from the audience? No. I will start the people can start thinking about the questions. Like, for example, I have a student, and I found your work on robustness very interesting. I have a student who presented here in the workshop. He's working on robust segmentation of medical instruments. I think it's a challenge by Lena Meyer. I think you work with her, and I think that's a very important kind of challenges that the medical community is tackling. And I don't see that happening in the normal, let's say, normal computer vision community. Can you tell us why?
So, why?
Yeah, like medical, obviously, you understand the challenges, and you understand which are the outcomes or not taking seriously the performance of a computer vision system. But what do you think that the people in the computer vision community are just so obsessed with going after just improving the metrics, but they don't really seem to care that much about robustness, for example?
Indeed. So I think the awareness on vulnerabilities against adversaries is growing both in the medical and in the computer vision community. So in both domains, I think it is critical. You were mentioning robotic surgery, what is called virtual endoscopy. And there, of course, if your robot is hijacked, then it can have very serious consequences. In the same sense, within the computer vision community, there are critical applications in which, adversarial robustness can really make a difference. One of them is self-driving cars. We have seen those methods that fool optical flow. Just with a printed patch, you can fool a very sophisticated optical flow system. That is a real issue, and I think it is being taken seriously within our community. And also another critical application is face recognition. There also, I think, adversarial attacks have a lot of saying to improve and to design the next generation of these systems.
Okay, perfect. So I see somebody, Maria Escobar, saying great talk. Thank you. I think I also found very, very interesting. Any other questions, people from the audience? Okay, let me think about. Okay, I see a question here from Fabian Cava. Great presentation. For the general vision task, it has been shown that getting ground truth consensus is hard. Yeah, this is particularly hard. Do you think in the healthcare domain this is even harder? What can you tell us about consensus?
Of course. One would think that the consensus is very high among these trained specialists, but also the tasks they address are very hard and fine-grained. When you think of segmenting a brain tumor, for instance, or detecting a lung nodule in a 3D scan, well, the failures by trained practitioners are more common than one may think. So there is really a need for automated methods within the healthcare domain.
Yeah, completely agree. Well, I think that we might have a time for another questions. Anybody else? Go ahead. Don't be shy. Yeah, it's sometimes kind of difficult in these virtual modes.
I know, yes. We all miss meeting at CVPR.
Meeting each other. So if there are no other questions, I just want to say, Pablo, thank you a lot again for your presentation. And we hope to see you on the flesh next time.
Thank you very much. Thank you very much to everyone in the audience. Have a great conference.